In this video, we'll be looking at tricks to avoid making a substitution. Or as I like to think of it, we're making a mental substitution. So sometimes an integral requires a substitution, but it might be simple enough that we can actually do this mentally. And in this video, we're going to have a look at a few types of or forms that can pop up in which making a mental substitution could save us a bit of time. Now, of course, you never really have to make a mental substitution. You can always do it on paper, show all you're working out, that's fine. However, in these particular types, sometimes it's easy enough for us to see, and so it's okay to actually do it in your head. So the first form that we're going to look at is the one that's written in blue. It's the integral of f dash of x times f of x to the power n. Now, let's have a look at an example. In this example, we're integrating cos x times sine cubed of x. The first thing that pops out to me is that we have some function being raised to a power. So if you look at it, sine is just like our f of x, and it's being raised to some power. And that, in this case, this power is 3. Now, if I have a look, I'm also multiplying that thing by something, and that's cos x. But if I'm really careful, I can notice that the derivative of f of x, or the derivative of sine x in this case, is actually that thing that I'm multiplying it by. It's cos x. So cos x is the derivative of sine. So this is really acting like our f dash x or f prime x. So here I have actually pretty much done my mental substitution. If I can recognize that it's of this form, I can go ahead and write the answer straight away. It's going to be f of x, which is sine x, to the power n plus 1. Well, in this case, 3 plus 1 is going to be 4, so it's to the power 4, divided by the new n plus 1, which is 4, and then plus c. And that's it. That's all we have to do for that one. We didn't have to make the substitution u equals sine of x. Our second example is an interesting one. We have the integral of x times the square root of 4 plus x squared dx. Now, usually when we deal with integrals where we have something of the form square root of a squared plus x squared popping up in the integrand, what we tend to do is we like to make the substitution x equals tan theta. And that's because this then turns into the square root of a squared plus, oh sorry, that should be a tan theta, a squared tan squared theta, and then this simplifies quite nicely using a few trig laws to a sec theta. However, in this case, I would like to think of it in a different way. Let's have a look at our integral. Let's rewrite that very carefully. Let's write it as the integral of x times 4 plus x squared to the power of a half dx. Now, the reason I do that is because now I have it in that form where I have some function, f of x, and that's being raised to some power. In this case, it's the power a half. But what is the derivative of the function? The function is 4 plus x squared. And if I differentiate that, I get 2x. Now, I don't have a 2x, I only have an x out the front. But that's not a problem. I can just multiply. What color should we use? Let's use blue. I can multiply by 2 and then by a half. And I've done nothing to the overall value of the function, or of the integral. But what I have done is I have created this f dash x here. I've created the derivative of my function. So now I can go ahead and use my mental substitution. It's going to be a half, which is the half that's sitting out the front. Now I'm going to raise f of x by 1 power, or the power of f of x by 1. So a half plus 1 will give me 3 halves. And then I divide by the new power 3 halves plus c. Now a half times 1 over 3 on 2, that's just going to give me 1/3, 4 plus x squared. Now because it was written in surd form, it's probably nicest to write it again in surd form. So this will be the square root of 4 plus x squared, or cubed, and of course plus c. And that's our final answer. We've avoided making a trig substitution. Our second form, or second type, of mental substitution is the integral of f dash of x times e to the power f of x. Now, whenever you see an exponential being integrated, unless it's an exponential to a linear power, so a polynomial with degree 1, unless it's exponential to a linear power, it's actually quite difficult to integrate these. Sometimes it's actually impossible to integrate these. So whenever you see the exponential being raised to a function which is not a linear function, you really should be looking for its derivative to be multiplied by. Now usually, if that is the case, that's going to indicate that we need to make a substitution. If it's not the case, probably the only other technique that you learn is at this stage is integration by parts, which is something that we'll see later on. So with this first example, we have the integral, or the third example I should say, it's the integral of sec squared x times e to the power 10x. Now, here I have an exponential to a power which is not a linear function, or not a linear polynomial I should say. It's f of x. Now, it's tan of x. So if I say f of x equals tan x, well, what's the derivative of this power? The derivative of our f of x is going to be sec squared, which is exactly what we have multiplying this exponential. So what we have here is e to the power of f of x being multiplied by f dash of x. And we can go ahead and make our mental substitution, or if you like to think of it, we're just using this rule. It's going to give us e to the power 10x plus c. It's just e to the f of x. In the next example, we have the integral of e to the power log x divided by x. So again, we can see that we have an exponential to a non-linear polynomial power. In fact, our power is going to be our f of x, and that is log of x. Now, if we differentiate log of x, we get 1 over x. Now, you might be able to see that this is going to be in this mental substitution form, but if not, we can actually rewrite our integrand in the following way. Instead of dividing by x, we can write it as multiplying by 1 over x. So this is 1 over x times e to the power log x. And now it should be much more clear that this is in fact e to the power f of x, and this is f dash of x. So we can go ahead and make a mental substitution, and the answer is just going to be e to the f of x. So e to the power log x plus our constant. Our third form is something that should be familiar to everybody that's doing the Extension 2 course. It's the integral of f dash of x over f of x. And this is, of course, the natural log of f of x. This is something that you should see in the advanced course. So it really isn't new content. It should just be a bit of revision, but it's good to do a bit of revision. So our first example is the integral of 1 over x times log x. Now, if we have a look at the denominator here, we have a function which is x times log x. However, when we differentiate that, we don't get 1. So at first sight, this doesn't look like it's going to be a log application. However, if we're clever with the way that we write our integrand, you'll see that this is the integral of 1 over x all over log x dx. And now it becomes clear that this is indeed a log integral, because we have our function f of x, the denominator, which is log x, and the derivative f dash of x, which is 1 on x, that's actually our numerator. So this is indeed a log function. It's going to be log of the denominator, which happens to be log of x. So log of log x plus c. This next example is quite an interesting one. At first sight, this looks like it's going to be what's known as a partial fraction decomposition. So what we would normally do is we would write 1 over x cubed plus x. Well, we can factorize our denominator. We would write that as x times x squared plus 1. And then we would try to write this as two separate fractions, one with a denominator of x and the other with a denominator of x squared plus 1. Okay, and we'd have to actually work out what these numerators are going to be. However, if you're very, very astute and it's probably pretty difficult to see this without actually having seen it done before. What we're going to do here is we're actually going to multiply the top and the bottom by x to the power negative 3. Or in other words, we're dividing top and bottom by x to the power 3. So let's have a look what happens. Well, if I divide the top by x to the power 3, that's just going to give me x to the negative 3. What about the denominator? Well, that's going to give me 1 plus x to the negative 2 dx. And here comes the genius of this. If you differentiate the denominator, what do you get? So we have f of x is equal to 1 plus x to the negative 2. Let's differentiate that. The derivative is going to be, well, the derivative of 1 is 0. Differentiating this will give us negative 2x to the negative 3. Now that looks remarkably similar to what we have in the numerator. In fact, we're only off by a factor of negative 2. So if I multiply the top by negative 2 and then divide by negative 2, I haven't changed the integral, I haven't changed its value. But what I do have is I have a fraction where the denominator is some function and the numerator is its derivative. I actually have a log integral here. Let's change to black. So this is going to be minus 1 on 2 times log of the denominator, which is 1 plus x to the negative 2 plus c. And that's actually our final answer. The last form that we're going to look at is the integral of f dash of x divided by the square root of f of x. And in this particular case, we're actually going to prove this standard form here. So the way that you can prove this one and all the other ones is actually to take the right-hand side, or take the answer, differentiate that, and see if you get the integrand. So what we're going to do, we're not going to take exactly the answer, we're just going to take the square root of f of x. So I want to have a look at the derivative of the square root of f of x. Now, of course, when we take derivatives and we have surds, we like to write those as exponents, as indices or as powers. So that's going to be f of x to the power of a half. All right, and when we differentiate that, that's just going to be the chain rule. We bring down the half, we take 1 away from the power, so that it will become negative a half, and then we also have to multiply by the inside derivative, which is going to be f dash of x. Okay, now let's multiply both sides here by 2. So when we do that, we get 2 times the derivative of the square root of f of x, and that's going to be equal to, well, this negative power means it's going to move to the denominator, so we have f dash of x on top divided by the square root of f of x. Okay, the half means the square root, the negative means it goes down, and now we're just going to integrate both sides. And while I do that, I'm also going to move this 2 inside the derivative, okay, because it's just a constant. So when I integrate a derivative, that's just going to give me the square root of f of x, and I have that 2 that's sitting at the front, and then it's going to be the integral of f dash of x over the square root of f of x dx. Okay, and now because I have an indefinite integral, it's going to be whatever my answer is plus any arbitrary constant, okay, because we actually get a family of integrals. So what we've done is we've actually just proved this formula. Let's now use it in an example. Okay, so here we have the integral of x divided by the square root of x squared plus 1. Now, if you think back to the earlier videos, we saw what happens when we have a quadratic underneath a square root in the denominator. However, that was if we didn't have an x in the numerator. That was only if we had a constant. Here we do have an x in the numerator, so we might start to think about that form that we were looking at, f dash of x over the square root of f of x. So in our case here, f of x is going to be x squared plus 1, and the derivative of that is going to be 2x, which is similar but not exactly the same as what we have, but that's not a problem because we can just multiply by 2 and divide by 2. So here, what we're actually going to get, we can straight apply our form, our mental substitution, is going to be a half times, now what was it? It was 2 root f of x. So a half times 2, the square root of f of x. What is f of x? F of x is x squared plus 1, plus our constant. But of course, a half times 2 is just 1, and so we get the square root of x squared plus 1 plus c. Okay, and that's our final answer. And that's actually the last example of this video. So what I would like you to take away from this video is that we can do some integrals which need substitution in our heads if we're confident with it. If we're not confident with it, then it's okay to just do the normal substitution. But as you can see with something like this, it only took 2 lines. Some of the other ones only took 1 line and were able to write out the answer straight away.